My people, we're doing well. Let's go ahead and jump right in. We are going to be doing related rates over the next few days, and I've decided this year I'm going to chop it up, especially since we're doing things virtually at present. And I think that that's going to help us get our head around exactly what related rates are about, because we'll focus on sort of one subgenre of the word problems at a time. And so for the ones today, we're going to be focusing on right triangle problems. So, and Pythagorean Theorem, basically. So you won't have to sit there and puzzle away as to what the formula is that you need. It'll be, x squared plus y squared is equal to z squared. And that'll sort of free us up to talk about the related rates aspect of related rates rather than sort of the figuring out the formula for the geometry of it, or, whether it's geometry or not. Okay. But this comes after implicit differentiation for a reason. We need implicit differentiation, the mechanics of it, in order to go ahead and execute some of these problems. And so just a little bit of a short chat about implicit differentiation and how it is done and how it can be done will sort of lead us into this. Now, let's say that we're given just a simple equation like x squared minus y squared is equal to 16. Now, you should recognize that as a hyperbola, okay? And we need to differentiate that implicitly. And so, if we're going to differentiate with respect to x, as we so often do, then this becomes 2x minus 2y dy dx is equal to 0. Okay, well, that's easy enough. And every once in a while, teachers and books teaching implicit differentiation kind of go, okay, and they throw a curveball at you and they go, okay, well, what if we differentiate with respect to y? Well, if we differentiate with respect to y, the relationship flips, right? It is y that agrees with this, and it is x that doesn't. So it becomes 2x dx dy minus 2y is equal to 0. Because when the variables do not agree, as the x does not agree with the y in this one and the y does not agree with the x in this one, there's a chain rule logic that has to be enacted, right? When I differentiate x squared with respect to x, it's just, and actually, I guess you could put 2x dx dx, right? But the dx dx is 1, so it sort of falls out. Here, when it goes to y squared, you get 2y dy dy, but dy dy, anything over itself, is 1. When it doesn't agree, you have to basically put something to represent the rate of change of that implied relationship of the one variable to the other. And actually, the thing is that you can differentiate with respect to anything. I mean, you can differentiate with respect to z if you want. And so we get 2x dx dz minus 2y dy dz. And of course, for this to be, mechanically, this is pretty straightforward. For this to be meaningful, there would have to be some variable z that has some relationship to x and y. Otherwise, this is just sort of an exercise in mechanics, and that's fine. Now, let's say, let's differentiate with respect to t, and we get 2x dx dt minus 2y dy dt. And I think you're kind of getting it. At this point, basically, I could differentiate with respect to q, and when I differentiate with respect to q, the only question is not can I do it, which I obviously can. The question is, once I've done it, does it actually say anything meaningful? Does Q represent something for me that has an implied relationship to x and y such that dx dq stands for some sort of rate of change, right? Okay, well, this is the mechanics of it. And the fact that you don't have to differentiate with respect to x, you don't even have to differentiate with respect to one of the variables that's there. You can differentiate with respect to a variable that actually is not present within the equation itself. Okay, so sort of hold on to that idea, sort of put a pin in it, I guess. and we're going to talk about right triangles. Okay. Now, like I said, to try to make things easier, I'm going to break the section down into sort of subgenre, subcategories, and we're going to be doing word problems that involve us setting up a Pythagorean relationship based upon a right triangle. So, we're going to be reading word problems, we're going to be setting up right triangles, and basically setting up equations with respect to those right triangle relationships. Now, one thing that we need to remember is, and this, when I say it, it's kind of like, oh yeah, that kind of makes sense. When we actually state the Pythagorean theorem, and of course this is x, y, and z, when I state the Pythagorean theorem, I'm actually stating that the three sides have this necessary relationship to each other. And so as long as it's a right triangle, this necessary relationship holds. Okay, but let's say, just for giggles, that I take this original triangle and I grab onto B and I stretch it out, okay? I leave it here and it's still a right triangle. It's still x, y, and z. I've just changed the triangle, right? Okay, well, despite the fact that the triangle has been changed or is in the process of changing, does not negate this necessary relationship. But it should also make sense that because the measurements have this necessary relationship, the rates at which they change will also have a necessary relationship to each other. Okay, and that necessary relationship will wind up being the derivative of the original equation, the original formula, in this case, the Pythagorean theorem. So, if we are given x squared plus y squared is equal to z squared, and we want to differentiate it because anytime you change something, you're changing it, like if I change that triangle, I'm changing it with respect to time, right? I'm elongating I'm elongating those sides at a particular rate, and therefore it's changing with respect to time, so I'm going to be differentiating with respect to t. And when I do that, I'm looking for d dt, right? And it's just an operation like anything else, and what I do to one side, I must do to the other. And then I just do it term by term, but noting that none of the three variables that are there actually are t. They have an implied relationship to t, but they aren't t. So it becomes 2x, so x squared becomes 2x dx dt, and y squared becomes 2y dy dt, and z squared becomes 2z dz dt. Now, of course, in the Pythagorean, all of them are squared, and so all of them bring down that 2, and so predictably that 2 can be divided out and sort of cancels. But this winds up being the relationship for the right triangle that is changing. Okay. Now, in the one that I showed you where I was basically just pulling out and elongating, when I was pulling out and elongating this horizontal measurement, I was also elongating the z, but notice that y didn't change. Well, sometimes all three of them will change, sometimes only two of them will change, but the ones that of course don't change still have a rate of change. It's just that that rate of change is 0. So for the particular scenario that we started off with, this holds. It's just that dy dt, since y doesn't change, it has a 0 rate of change. All right, well, let's go ahead and jump in with some examples, and we'll sort of do these. We'll do all of these sort of according to the same method. Now, a ladder of 25 meters long, that's a long ladder, is leaning against a wall. The bottom of the ladder slides away from the wall at a rate of 4 meters per second. Everybody's worst nightmare when they're up on a ladder, right? So we have, the wall, and we have the ground, and we have this ladder, okay, that is leaning up against the wall. And this right here, this bottom starts to slip out going that way. Well, that means that the top, and we're assuming that the top maintains contact with the wall, is basically slipping down the wall. Now, that means that the distance from here to the wall is, of course, a variable that we'll call x. This right here, how far the top is from the bottom of the wall, is a variable we'll call y. Now, in this particular one, we know that the ladder is not going to be getting any longer or any shorter, and so it is 25. Okay, so obviously I'm going to be setting this up as x squared plus y squared is equal to 25 squared. Okay, now there are three things that a question stem will give us or ask us for, okay? The first is what I refer to as the givens. Now, these are things that do not change. They are constants, okay? And it's weird, but even, the ladder slides away from the wall at a rate of 4 meters per second, you're assuming that even though in and of itself it's a rate of change, that rate of change doesn't change. It's given. During the entire scenario, the bottom ladder slides away at 4 meters per second. Now, as the bottom of the ladder is sliding away from the wall, that is changing the magnitude of x. So it is the rate, what they're giving us here is the rate of change of x with respect to time. So they're giving us dx dt, and they're giving it to us as 4 meters per second. Now we need to be careful because 4 meters per second is positive here because it is making x larger, right? If they had instead given us how fast the top of the ladder was sliding down the wall, it would have given us the rate at which y was shrinking, and therefore it would have been a negative number. Now, we have this given information, and we don't put 25 meters here as a given because it actually it doesn't need to be plugged in anywhere but this equation right here. Now, it's also going to ask us a question. What are we looking for? How fast is the top of the ladder sliding down the wall? Okay, well, therefore, we've been given dx dt, and we're asked for dy dt. But we're not asked for dy dt in general. We're asked for dy dt at a specific moment. When. There's your key word. Anything that follows when, or is, predicated on that moment in time, that instant, will be part of, and I guess you'd call it instantaneous information, but I've always referred to it as conditional information. To tell you the truth, I really don't know if there's an official name for it, but as long as we're consistent with our nomenclature, it really doesn't matter. Now, it says, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 meters from the top, when the bottom of the ladder is 6 meters away from the wall. Okay, is the bottom of the ladder always 6 meters away? Of course not. It's moving, right? And so basically what it's asking for is, it's asking for as this scenario takes place and as the bottom of the ladder slips away, it's asking for, okay, I take a picture, boom, and at that moment, what is my dy dt when x is equal to 6? Okay, well, that shouldn't be too tough. But let's go ahead and let's differentiate this. Now I know that because I'm dealing with a scenario that involves this Pythagorean relationship, I know that when I differentiate with respect to t, I'm going to get the necessary relationship between the rates, right? They're called related rates because you're questioning how do the rates relate to each other. I know, it's staggering. It's almost like they name these things on purpose. Now, if we're looking for dy dt, you notice that both of these have a 2. They can sort of, go away. Now, I have a formula now. It's a different formula because I've differentiated it of 4 unknowns, and I'm looking for one of them. But it seems like I only have 2 other pieces. Now, if I have a formula of 4 unknowns and I'm looking for one, I necessarily have to have the other 3. But while I was actually given this conditional information, because at that moment it's still a right triangle, this 6 meters implies a particular measurement of y. And you just use Pythagorean Theorem, and you're going to get, of course, 25 squared is 625. And when you do all the Pythagorean Theorem with the 25 and the 6, you get y is equal to the square root of 589. Unfortunately, and the thing is that oftentimes when you're given something like this, they'll use Pythagorean triples, right? And I actually expected them to do that here. I expected them to have when x is equal to 7, because if x is equal to 7, then what you have is a 7, 24, 25 right triangle, and your y measurement winds up being an integer. But we'll go ahead and go along with the way that it's written right here. So now I do have 4. I just have this one right here. This one was what I usually refer to as implied conditional information. And that just means that, if you differentiate and are missing some information, there was other information implied by what was explicitly stated. You just have to go fetch it, okay? So in this case, we have x, we're going to go ahead and plug in 6 meters. dx dt is 4 meters per second. Your y is the square root of 589 meters, and now you're looking for dy dt, and that's equal to 0. So dy dt is equal to the negative of 6 meters and 4 meters per, so it needs to look like a 4, I guess. Square root of 589 meters. Now, these units and those units cancel out, and I'm left with negative 24 over the square root of 589 meters per second. And that right there. Now, remember, I told you that if it was sliding down the wall, it was making y smaller, and therefore it makes sense that dy dt is indeed negative right here. And that's it. And it would have been different had your conditional information been a 7 right here instead of a 6, right? And let's go ahead. I guess I'll do that in a different color since it's a different scenario. Let's use green. Let's say instead it was x is equal to 7 meters, and therefore y was going to be equal to 24 meters because 7, 24, 25 is a Pythagorean triple. You would have had instead dy dt, and it would have been negative 7 meters, and still would have been 4 meters per second because that's a piece of given information, over 24 meters. The meters, again, cancel out, and you're left with, of course, this can cancel with this, and you're left with negative 7/6 meters per second. And of course, that's much tidier, and basically all that is, the difference is basically just different conditions, right? And that goes to show you that it's not, if dx dt is a constant, that doesn't mean that dy dt is, right? Because it's obviously not. These are two different numbers, okay? Now they're both right around -1, or at least close, but they are distinct numbers, okay? dy dt is this, and actually let's go ahead and approximate that. We have negative 24 divided by the square root of 589, and that is going to be approximately 0.989, negative, of course, meters per second. And negative 7/6 is, it's going to be negative 1.167 meters per second. So it's obviously speeding up, right, as it's going down, because when x is 1 meter, when it is slid 1 more meter away from the wall, sort of at a future time from x is equal to 6, the rate at which it's coming down the wall is going to be greater. It's going to have a greater absolute value, a greater magnitude. Alrighty, let's go ahead and do another example. By the way, this is a very classic one when everybody who does related rates sees the latter problem multiple times, okay? And that's one of the classics. This is another one of the classics in terms of right triangle related rates. This one reads, a helicopter flies parallel to the ground at an altitude of 0.5 kilometer and at a speed of 2 kilometers per minute. If the helicopter flies along a straight line that passes directly above the White House, at what rate is the distance between the helicopter and the White House changing 1 minute after the helicopter flies over the White House? Okay, now remember, not an artist, okay? So here is the White House, and here is the helicopter. Yeah, I know, I'm terrible, but deal with it. And basically what you have here is you have, and I'm just, obviously, let's go from tip to tip. You have a right triangle. Now it says that the helicopter is flying parallel to the ground. So this right here is always 1/2 of a kilometer. This right here is going to be my x, and this right here is going to be my z. Because as fast as the helicopter, and you could have, done the triangle where the base was up here and stuff like that, because, basically as fast as, if it's flying parallel to the ground, as fast as it's, charting out x distance up here, it's also doing it down here. So, 2 kilometers per minute. So the helicopter is flying at 2 kilometers per minute. That is dx dt. Now, it is after the helicopter passes the White House. So it is basically the helicopter is now moving away from the White House, and therefore this x is getting larger. So the 2 kilometers per minute is actually positive. If it had been charting, the helicopter as it was going toward the White House, then obviously the dx dt would be closing that distance, making it smaller, and our dx dt would be negative. Now, it's going to ask us for what rate is the distance between the helicopter and the White House changing? There's our question. And the distance, obviously, is this z. Okay, so it's asking for dz dt. Now, it's not asking for that in general because it can't. But it's basically saying at what rate is the distance between the helicopter and the White House changing 1 minute. Okay, so basically there's an implied when right here. Okay, 1 minute after the helicopter flies over. Okay, well, that's giving me a designation of time. That doesn't give me a distance. Well, distance equals rate times time. So that moment in time, 1 minute after the helicopter, if it travels 2 kilometers per minute and it's been traveling 1 minute since it passed over the White House, then the conditional information is x is equal to 2 kilometers. Okay, well, it doesn't tell us what our z measurement is at that moment, but it's easy enough to find out, right? All you would have to do is 2 squared plus 1/2 squared, so that's 4 plus 1/4. 4 plus 1/4 is 17/16, so z is equal to root 17 over 4 kilometers. And if you have to actually work that out on the piece of paper, that's fine. So remember that I've called this right here something which I go and fetch after I look at the conditional information, but isn't stated explicitly as my implied conditional. Okay, well, now I have enough information where I feel comfortable going ahead and setting it up. And it's x squared plus 1/2 squared is equal to z squared. And when I differentiate and then multiply through by 1/2 or divide through by 2, I get x dx dt is equal to z dz dt. And if I'm looking for dz dt, I'm looking for x times dx dt over z, which in this case, I have all three pieces of information. I have dx dt is obviously from my given, and I have my x and my z measurements. At the moment, it is 1 minute past the White House, and so this becomes 2 kilometers, and this becomes 2 kilometers per minute. This becomes root 17 over 4 kilometers. Now the kilometers obviously are going to cancel out. This is going to wind up being 16 over root 17 kilometers per minute, right? Because to divide by root 17 over 4 is to multiply by 4 over root 17. 4 times 4 over root 17 is 16 over root 17. And root 17 is a little bit more than 4. So 16 divided by a little bit more than 4 should be a little bit less than 4. Let's go ahead and look at that. So we get 16 divided by root 17. Yeah, a little bit less than 4. So we get 3.881 kilometers per minute. Now, I didn't stop on the last one and put it into the final form that it should be in. But anything that is asked in sentence form should be answered in sentence form. So basically you say, at 1 minute past the White House, the distance between the helicopter and the White House is increasing, because z is getting larger, at approximately 3.881 kilometers per minute. And that is the appropriate way to answer. And we're done. Okay. Now, we're going to go ahead and call this one to a close. We have 1 or 2 more videos, depending on how long these others take me and what kind of rabbit trails I want to hunt down. But I'm hoping that these videos, along with the classroom time that we had together, will help us to understand related rates. First of all, simply because these aren't changing. They're all right triangle problems, and therefore we're sort of taking that layer of complexity away, and we're just seeing how the different measurements of right triangles change with respect to each other when we differentiate the Pythagorean theorem equation or formula. And so we'll do a couple more, and tomorrow, like I said, we'll move on to further examples of two-dimensional geometry before moving on to three-dimensional geometry and trigonometry and all sorts of fun stuff like that. But if you have any questions, please do shoot me an email. Bye.